Hi, my name is Josiah Radcliffe, and in today's project I will be exploring the effective stiffness as well as the period of oscillation of two mass spring systems. To start off, let's go ahead and look at the apparatus setup. Here we have the setup for this project. We have the spring mass system using the two magnetic hooks attached to a metal bar on this bookshelf. We can hang the masses from the bottom spring, and on the left we can even attach a plastic ruler with magnets to the bookshelf so that we can measure the static displacement. Masses can be added one by one, but for the sake of time, I'll just show that we can add all of the masses at once. We can see the static deflection, and then we can measure it based upon a reference point, in this case, the bottom of the hook. We do the same thing for the large spring, adding all the masses. We can see the dramatic difference in the static displacement measured on the ruler. If we move the ruler to the side, we can set the system in motion, and over the course of a minute, count the number of oscillations to determine the period. Well, we know that the stiffness of a coil spring is inversely proportional to the number of coils, which relates to the length of the overall spring, and then also inversely proportional to the diameter of that spring cubed. That means for a spring with larger diameter or longer length but of the same material and gauge wire, the larger spring would be less stiff. For today's project, I use MATLAB to plot the small spring and the large spring static displacement response. So we can see that the shape of both plots is extremely linear for all except the first few data points. This confirms that the springs do obey Hooke's law. The nonlinear portion near the equilibrium point indicates that more force is required to start the stretching of that spring at small displacements. So here in the plot, we see the small spring in blue and the large spring in red dotted lines. Using a polyfit function in MATLAB, a line of best fit can be applied to the data, and the slope of that line can then be used as the spring stiffness once we multiply it by the acceleration due to gravity, since this is only a plot of mass times displacement and not force times displacement. The stiffness of the springs is related to the slope of those lines. We can see that the small spring in blue has a steeper line, higher slope, and therefore a larger stiffness, which confirms what we predicted earlier about the effective stiffness of the springs. So now let's move on to the second part of the project, where we looked at the period of oscillation for both spring mass systems. So what we'll look at first is this middle column, the measured value of the period. The top value we see is the small spring, and the bottom value we see is the large spring. The small spring had a shorter period of oscillation, which was to be expected due to the higher stiffness. The two values to the left and right that we see here are the calculated values. The one on the left is the calculated value without including the effective mass of the spring itself. And on the right, we have the value calculated using the effective mass of the spring, which is 1/3 the mass of the spring plus the mass of the mass attached to the system. The measured and calculated results for the smaller spring were very accurate, within 0.6%. Using the effective mass of the spring, the error was reduced even further to 0.37%. However, for the large spring, we see a significant error between the calculated without the effective mass value and the measured value. However, we see a much reduced error for the measured versus the calculated value with the effective mass of the spring. There was some error in the estimation of the slope of the best fit line, as can be seen from the graph that we showed before, where the black line that matches up with the small spring data is very accurate, but the green line that matches up with the red spring data has some more error. Additionally, the large spring has a higher mass than the small spring, meaning that the way it affects the system will be more significant than the small spring. The larger spring, having more mass to contribute to the effective mass, results in a larger error between the measured and calculated values, with an error of 6.26% between the calculated without the mass of the spring and the measured. However, when the mass of the spring is included, the error is significantly better at only 0.64%. Including the mass of the spring had a minor but improving effect on the small spring, but had a significant effect on the comparison of the measured and calculated values of the large spring.